All right, this is my third video where we're talking about how to use matrices, in particular augmented matrices, to solve systems of equations. In the last video, we solved this problem here, and basically we took the original matrix, that's this one here, and we used row operations to get to this matrix here, which is in what we call row echelon form, where we have ones on the main diagonal and zeros below the ones. Now if you have zeros above the ones, then we call it reduced row echelon form, and that's what I'm about to do. But what we did previously is we took this matrix and we wrote a system and then we used back substitution to find our solution. And so this is the way that I prefer to teach students the first time I show them matrices and show them how to use matrices to solve systems in this way. But I'm going to go ahead and show you how to keep going and take this matrix into reduced row echelon form. So we're trying to get zeros above the ones here. So what we're going to do, it's kind of the opposite of the way we started. Originally we got a 1 here and then we used it to get zeros below, and then we got a 1 here and we used it to get a 0 below there, and then we got this 1 here. So that was the last thing we did. Now the one we just got we're going to use to get zeros in these two positions here. And so I'm going to go ahead and multiply, hold on just a second, I'm going to multiply the third equation by -3, and I'm going to add that to the second equation to get a 0 where that 2 is. And then I'm going to multiply the that's going to give me my new row 2. And then I'm going to multiply the third equation by -3 and add that to row 1, and that's going to help me to get a 0 in this position here. And so let's go ahead and do that. So I'm going to rewrite the matrix, and the third row doesn't change, but the other two will. So I've already put in the third row. So if you multiply -2 times row 3, you would get 0, 0, -2, and -2. And so now I'm going to add these values here together. I'll get 0 plus 0 is 0. 1 plus 0 is 0. Excuse me, 2 and -2 is 0. And 1 and -2 is -1. And so I'm going to need to do a little bit of erasing here. And now I'm going to multiply, we'll get that first row, we're going to multiply -3 times row 3, and so we'll get 0, 0, -3, and -3, and I'll add these numbers to the first row. And so 0 and 1, we're still going to have 1. 0 and 2, that's going to give us 2. -3 and 3, that's giving us the 0 that we wanted in that spot right there. And -3 and 4 gives us 1. And so notice we now are almost done, because the only thing we have left to do is that first row. We have a 2 in the second position, and we need to have a 0, so we are in reduced row echelon form. And so what we're going to do is, so notice we just got the 1 here. Actually, we didn't just get the 1 there, but we used this 1 to get these zeros here. And so now we're going to use this one. It's like we're moving back up the diagonal. We'll use that one to get a 0 where the 2 is. And so I'm going to go ahead and multiply -2 times row 2 add that to row 1, and that'll become my new row 1. And so let me go ahead and write the matrix with the last 2 rows. The first row is the only row that's going to change. And we're going to do -2 times row 2. So 0 times -2 would just be 0. 1 times -2 is -2. And 0 times -2, of course, is 0. And -2 times -1, we're going to get 2 here. And so now we're going to add these numbers together. The red values I have in row 2 added to row 1. So we have 1 and 0. That's going to give us 1. And then 2 and -2 will give us the 0 we were looking for. Of course, 0 and 0 is 0. And 2 and 1, we're going to get 3. And so now we're finally done. This is completely in reduced row echelon form. And so you can see that x equals 3, y equals -1, and z equals 1, which is what we originally got. So basically, here's what it comes down to. If you like the way that I originally did this, where we got row echelon form, and then we use back substitution to solve the system, you could do that, or you could continue like we did here until you get row echelon form, I should say reduced row echelon form, and you can see once we have that, we have our solution. So either way is fine, and I really think it's just a matter of personal preference. They're both good techniques. Let's move on to our special cases. So in number 14, we're going to do what we were doing previously, and you're just going to find that in these 2 problems, we're going to be dealing with our special cases. So let's go ahead and write the matrix that corresponds to this system here. And you can see I've got the 1 that I need right there. I need zeros below the 1. And so we're going to want to multiply the first row by 3 and add that to row 2, and that'll be our new row 2. And then we want to multiply the first row by 2 and add that to row 3, and that'll be our new row 3. So let's go ahead and rewrite the matrix. The first row is not changing, so I wrote in the first row. And let's go ahead and multiply each element by 3 in the first row. So 3 times 1 is 3, and we'll get 3. 3 times -2 is -6. And 3 times 5 is 15. Whoops, and so now we can add these numbers together. 3 and 3, -3 is 0. 3 and 3 is 6. -6 and 4 is -2. 15 and 6 is 21. All right, and so now we're going to multiply the first row by 2 and add that to row 3. So let me go ahead and erase those values and multiply everything by 3. So we'll have 3, 3, -6, and 15. And we're going to add those values to the third row. Oh, wait a second, that's not right. I was supposed to multiply by 2. So it'll be 2, oops, 2, 2, -4, and 10. And so now we'll add these values together. So we're going to get 2 and -2 is 0, 2 and -2 is 0, -4 and 4 is 0, and 10 and 10 is 20. Notice this is a false statement that we have in this last equation. 0x plus 0y plus 0z equals 20. That's 0 equals 20. That's a false statement, which means there is no solution. We should probably write false in here. So this system does not have at least one solution, so it's inconsistent. And this is also an independent system. All right, let's move on to number 15. So here, let's go ahead and write our matrix. And again, you can see that we have the 1 in the upper left-hand corner. And so we can use that 1 to get our zeros below. Let's do that first. And so it'll be row 1 added to row 2. That's kind of nice. That'll be our new row 2. And negative 2 times row 1 added to row 3, that'll become our new row 3. So I'm going to go ahead and put in our new matrix with the first row since it doesn't change. And let's go ahead and add the first and second rows together. So here we have negative 1 and a positive 1. That's 0. Then negative 1 plus 3 is 2. Negative 1 and negative 5 is negative 6. 1 and negative 5 is negative 4. And then let's multiply the first row by negative 2, and we'll add that to row 3. So we'll get negative 2, 2, 2, and negative 2. So that's the first row multiplied by negative 2, and we'll add that to row 3. And we're going to get negative 2 and 2 is 0. 2 minus 1 is 1. 2 and a minus 5 is negative 3. And negative 2 and 0 is negative 2. Now, again, you might be tempted to switch row 2 and 3 so that you can get the 1 that we need where the 2 is. But it actually is pretty easy to just divide the second row by 2, which is equivalent to multiplying by a half. So a half row 2 becomes our new row 2. Again, I'm going to write the matrix with the first and third rows since those don't change. And row 2, we're just dividing everything by 2. 0 divided by 2 is 0. 2 divided by 2 is 1. Negative 6 divided by 2 is negative 3. And negative 4 divided by negative 2 is, by 2 is negative 2. So hopefully you notice, hey, the last two rows are the same. This is going to be our solution where we have infinitely many solutions. We're going to get 0 equals 0 here. Let's go ahead and add the opposite of row 2 with row 3. And so I'm going to go ahead and rewrite the first two equations. First two rows, those don't change. And let's switch our signs. Did I do that? No, I didn't do that. Well, in the second row, we're just basically applying or multiplying by negative 1. Well, 0 times negative 1 is still 0. And then on the others, we're just going to switch the signs since we're multiplying by a negative. And so now when we add, we're going to get all zeros, aren't we? Whoops, how did I miss this 0? And so we get 0 equals 0. This is the case where we have infinitely many solutions. But again, there's a way that we can be a little more specific in writing out our solutions. And so let me go ahead and write the equations that correspond to this matrix. We've got x minus y minus z equals 1, and y minus 3z equals negative 2. We don't really need to put in the 0 equals 0 here. It doesn't help us. So here's the idea. We're gonna let z, the variable z, represent z. And then if we could solve y and x in terms of z, then we'll be able to write the general point for solutions to this system. And so let's go ahead and solve for y. We get y equals 3z minus 2. And so in the first equation, I'm going to replace y with 3z minus 2. And of course, z I don't have to change because z is the variable we're representing z with. So we're going to have x minus 3z minus 2, that's our y value, minus z equals 1. And so let's go ahead and distribute the negative here. We get x minus 3z plus 2 minus z equals 1. And let's simplify the left side here. We can combine our z terms. We'll get x minus 4z plus 2 is 1. And I'm trying to get x by itself, so let's add 4z to both sides and subtract 2 on both sides. On the left, we get just x. And on the right, we're going to have 4z minus 1. And so notice everything's in terms of z here. We know y in terms of z and x in terms of z. So if we call our z value the variable z, then y would be 3z minus 2, and x would be 4z minus 1. And so all the solutions, these infinitely many solutions, have this form. And basically, if I wanted to get a solution, I could just plug in a value for z and figure out what x, y, and z would actually equal for one of the solutions. Okay, so I do want to say that this has infinitely many solutions, so it's a consistent system. And this is the case where these are the same line, and so this is the dependent. Ooh, I said independent. I should have said dependent here. Let me fix that. This is the dependent case, and just as an example, or let me see if I did that. No, I guess I stopped there. So basically, if I let z be 0, let me change colors here. If z were 0, then y would be 3 times 0 minus 2. That would be negative 2. And if I put a 0 in here, 4 times 0, 0 minus 1, we get negative 1. And so the point negative 1, negative 2, 0 would be one of our infinitely many solutions. Now, we didn't ask you to find some exact points, but that's how you would do it. All right, so that's it for this last video on solving systems of equations using matrices.